Good afternoon, everyone. Am I audible? Okay. I'll share my screen then. We were doing the number 2 question, no? The second example. Okay. So, our question is this one. Here you have this beam which is fixed at one end and it is hinged here. It has a point load. It has a point load at L by 2. Okay. This is your L. This is your L. This is capital L. This is your L by 2. L by 2. Okay. Then we have, this is your hinge. Okay. So now you have to calculate this. For this, you have to calculate the collapse load. So what we have to do, we know according to the kinematic theory what? Our internal work is equal to our external work, right? And through that equation, we can find out our collapse load. So what will be this deflection here? If we draw now this one, this one, the deflection is here at the center. This is L by 2 distance. Right, this is L by 2, so our deflection will also be here at the center under the load, this one, okay. Then we have, okay, this is another one here. So now the reflection is here. We have this angle theta. This is L, you know already. This is L by 2, L by 2, and this entire is L. We have here, this is your theta. Since it is at the center, the point load is at the L by 2 distance from both the ends. So we can consider this to be, wait, theta. Okay. Here. So here also you will have what? Theta. This is your delta. The deflection is given by delta. Okay. So after that, yeah, what is this angle? Okay. Okay. So what is your this angle here? This will be also theta. Here, this will be theta. This will also be theta. Right. So now we can find out our this thing, the internal, what is our internal work done? What will be our internal work done now? What was our internal work done? Our internal work done was plastic moment into rotation. Okay. So MP, the plastic movement, where will that be present? Where you have the plastic hinge, right? Plastic hinge wherever it is present, and where it is present, your plastic hinge at fixed supports, your under the point loads, and when you have different geometry, certain change in the geometry, or when you have what, your any section changes geometry, and also at the point of zero shear, okay, in a span where we have a UDL. So here in this particular figure, how many plastic movements are there? Right. How many are there? There are, this is the fixed support here. So here we will have plastic hinge, and this is a point load which is your P. So under this also we have the deflection, and so here also you have a plastic hinge. But here this is not a fixed support, but this is a hinge support, so we have no plastic hinge here. So what will be your internal work now? Because we have how many? Two plastic hinges here, for which we will have a plastic moment here due to this fixed support and also due to this point load. So what will be your internal work done? your internal work done now for this will be MP into your angle theta, because we know our internal work done is what? Our internal work done is your plastic moment at the plastic hinge into your rotation, right? So what will be your this? MP, here your moment is how much? MP. So let me change it to green. So you will have here capital M small p, that is your plastic moment into what you have, the theta, and I was giving the theta to be how much? At the rate. Okay, so we have MP into theta plus we will have, here we have a plastic hinge, so we will have again one MP. Okay, I'll give in bracket MP into, we have here how many thetas? The angle, the rotation here is theta plus theta, this theta plus this theta, that means 2 theta, this one. Okay, and here we don't have any plastic hinge, so there is no plastic moment. So now what will be our total, sorry, what will be our total work or the internal work? 2 MP theta plus 1 MP theta, that means how much? 3 MP theta. 3 MP theta, right? So now again we can calculate what? We will calculate now the external work done. So now the external work was how much? The deflection, force into deflection. And what is our force here? We have the force to be P into, I have to take the pencil. So P into delta, this one, P into delta. Okay, now to find out delta, again the same thing which we have done. We will take this triangle here. Okay, if we take this triangle here, how much we have? The theta, this thing, delta, how much? From tan theta, how much we got? If we take this triangle, this one, tan theta is equal to how much? Delta this one, delta divide by your this base is how much? L by 2. So we are having here capital L by 2. Okay, so from here we can easily get and we'll consider this angle to be very small, and therefore if it is very small, then tan theta becomes theta. So what will happen now? Your theta will be how much? Theta is equal to your this one only. Okay, your theta is equal to, that means your, since the angle is very small, so your theta is delta by L by 2, delta by L by 2. And so now what will be your delta? Your delta will be theta into L by 2, right? So what will be your this? P into theta into L by 2. Okay, okay. So now we have to find out the collapse load. We can use the theorem again, the kinematic theorem, which is your this load into this load, that is the internal load is equal to your external load. So you will have therefore 3 MP into theta is equal to P into theta into L by 2, right? So from here obviously we will have how much? We will have this, here we have the thetas are cancelled, Easily we can find out this load now. We need to find out the collapse load, and our collapse load is how much? Now our collapse load P is equal to how much? By 2. So it will be 6 MP 6 MP divided by your capital L. Right, from here we get our P is equal to 6 MP by L. So this is our collapse load. This is our collapse load. Okay, fine. Now, okay, I'll do one thing. I'll save this also. This is therefore our this collapse load is this much. Okay, I have saved this annotation. Now we'll take another question. Okay, now we will take another question. This was simple question, just basic for your when you have a fixed, and also when you have a fixed and a hinge, and also when your load is at the center, then this is simple and easy to do. Calculate this collapse load. Now we will do a problem. Okay, you can take the screenshot. I'll remove the annotations now. If you want, you can do the screenshot or you can note it down. Okay, we'll take another question now, the third number question. With different position of our point load, and with different point loads, and maybe it will be more than one point load. We'll try to solve that, how to solve that, and how to find out using kinematic theorem the collapse load. Okay, done. Okay, now we'll take the different question. Question number 3. Determine the collapse load in the so what is the figure? I'll show you the figure now. The figure would be, this is your beam. It is fixed on both the sides. So this is fixed. This is fixed. Okay. So you have point load is here, another point load is here. Okay. This one is your 1.5 L. Another one, this one is your 1.5 L, we have here L, 1.5 L. Okay, this is your W, the loads, two loads are there, W and W. These are your fixed. Okay, so these two are fixed supports here. We have at a distance of 1.5 L, we have this W. Another at a distance of L, we are having W. Okay. MPs are given to be MP. This one is given to be 0.5 MP. Here it's MP. This point we can consider it to be A. B, C, C, and this to be D. Okay, A, B, C, D, we have this here. So we have to find out the collapse load now. Okay, so let us start with the figure. How will be your figure? This is your figure, so we will have to draw the deflection here. We have, this is our beam, right? So we will have deflection under this point load B at B and at C. So here in this case there will be what? In this particular question we have 2 point loads. So therefore what will happen? There will be two possible collapse mechanisms. Okay. One is like before what we used to do, we had a point load at the center, so we had the collapse here at the deflection center, but now under the point load, right? But here we have two different point loads, two different, that means at different points we have the point load. So the deflected portion where this collapse may happen, we can consider it to be once here and on the other hand here also. Okay, so first of all we'll see if the this fixed beam is collapsing here at this point load. So for that we have to draw the deflection here. So let us draw. Here we are taking this. Okay, here we are having the deflection. Another one is this one, right? We can give here a dash dash. Under this deflection may take place here. Okay. We have the point load here, another point load here. This we can consider it to be, it was how much? It was W at the point B. So we can take it to be WB and this to be WC, WC, right? We have here point A, B, C, B. Here we have C. And this is D. Okay. We also have this one to show the bottom angles. Okay. So our angle will be here theta 1. We can consider it to be theta 1. This to be theta 2. Theta 2. Okay. And here we are having this angle will also become theta 1 plus theta 2. This will become what? Theta 1 plus theta 2. Okay. So now, okay, these things we know. This distance is 1.5 L. This is L. This is 1.5 L. Okay. So there are two mechanisms. Okay, two possible mechanisms of failure. Like it can be here at this under this point load, the deflection can be here, or we can keep it here also. So second, this is your first possible mechanism. Another one is here. I'll show you somewhere after we see this. We will think that the deflection is more here at this point, and it is collapsing here, or maybe less also, but it is collapsing here in this point. Okay, but for this first mechanism, we are considering the collapse is here. So here we have considered. Now what we have to do is we have to find out the deflection here. This we know, deflection and the theta we have to know, because with the help of that we can find out or calculate the collapse load, which is the where we have the internal work done is equal to the external work done. Alright. So what we'll do, see here, because here we have two different positions we have different load. So here is theta 1, here is theta 2. Earlier we had what? At the center we had the point load and the theta. Because it was at the center, our angle was also same. But here obviously the angles will be different, right? So what will happen? We have two different angles. So we have considered this to be point 1, the theta 1, and this to be theta 2. Okay, so but in this particular mechanism, what we are going to do, we are going to consider this to be theta, and suppose this or this, whichever you want to take. Okay, with respect to this angle, we'll find out with respect to this. So we will consider this to be, let us consider this to be equal to theta. This equal to theta. Okay, done. And we have here this distance is how much? This distance, since we are considering here to be the collapse, so we have to know this distance. This entire distance is how much? Because this was how much? L plus 1.5 L. That means 2.5 L. So this will be 2.5 L. This L plus this L is equal to this entire distance L, 2.5 L. This is, we know, 1.5 L obviously. So now we have to calculate this, right? So what we can do now? to find out, okay, one more thing. I forgot to say you that first two questions. Not forgot actually. We used to calculate the delta, the deflection with the help of, okay. Shall I continue with another class now? Or what? Okay, let me take the attendance first of all. Today is 11. Roll number 44. Roll number 44. 64.
64, ma'am. Present. 64.
65.
065 present, ma'am.
067.
Present, ma'am.
69.
Present, ma'am.
70. 72. 73.
73. Present, ma'am.
74. 75.
Yes, ma'am. 75.
76. 77. 78. 81. 82.
Present, ma'am. 82.
83. 84.
Present, ma'am.
85. 86. 88. 89. 91. 92.
92 present, ma'am.
93.
93 present, ma'am.
94. 94. 95. 96. 97. 98. 100. 102.
Present, ma'am. 100.
100. 110. 112. 115. 112.
112.
Okay, 115. 116. 117. 119. 121. 122.
Present, ma'am. Yes, miss. 122.
121. 122. 123.
Yes,
20,
ma'am. 123.
25. 26.
Yes, ma'am. 126.
27. 28. 130. 32. 35.
130, ma'am.
130.
Present. 130.
130.
Yes, ma'am.
135.
135.
135. 137.
130, ma'am. Yes, ma'am.
Okay, 137.
Yes, ma'am.
140. 139. 140. 142. 147.
142,
Okay, 147.
ma'am. Yes, ma'am.
Michael. Tasika. Laishram.
Present, ma'am.
Laishram present. Chasen.
Present, ma'am.
Okay. 132. Okay.
Ma'am, 110.
110. 121 present. 132. Shall I complete this problem now with another link?